6.8 Electron Configurations. Armed with knowledge of the relative energies of orbitals and the Pauli exclusion principle, we are now in a position to consider the arrangement of electrons in atoms. The way in which electrons are distributed among the various orbitals of an atom is called the electron configuration of the atom. The most stable electron configuration of an atom, the ground state, is that in which the electrons are in the lowest possible energy states. If there were no restrictions on the possible values for the quantum numbers of the electrons, all the electrons would crowd into the 1s orbital because it's the lowest in energy. The Pauli exclusion principle tells us, however, that there can be at most 2 electrons in any single orbital. Thus, the orbitals are filled in order of increasing energy, with no more than 2 electrons per orbital. For example, consider the lithium atom, which has 3 electrons. Recall that the number of electrons in a neutral atom equals its atomic number. The 1s orbital can accommodate 2 of the electrons. The third one goes into the next lowest energy orbital, the 2s. We can represent any electron configuration by writing the symbol for the occupied subshell and adding the superscript to indicate the number of electrons in that subshell. For example, for the lithium we would write 1s2, 2s1. We can also show the arrangements of the electrons as lithium, first 1s2 has 2 electrons, one pointed up, one pointed down, and the 2s orbital has 1 going up. In this kind of representation, we call an orbital diagram. Each orbital is denoted by a box and each electron by a half arrow. The half arrow pointing up represent the electron with a positive spin magnetic quantum number, ms equals positive 1/2, and the half arrow pointing down represents the electron with a negative spin magnetic quantum number, m sub s equals negative 1/2. This pictorial representation of electron spin is quite convenient. In fact, chemists and physicists often refer to electrons as spin up and spin down, rather than specifying a value for ms. Electrons having opposite spin are said to be paired when they are in the same orbital. An unpaired electron is one not accompanied by a partner of opposite spin. In the lithium atom, the 2 electrons in the 1s orbital are paired, and the electron in the 2s orbital is unpaired. Section 1. Huns rule. Consider now the electron configurations of the element change as we move from element to element across the periodic table. Hydrogen has 1 electron, which occupies the 1s orbital in its ground state. The choice of a spin-up electron here is arbitrary. We could equally show a ground state with a spin-down electron in the 1s orbital. It's customary, however, to show unpaired electrons with their spins up. The next element, helium, has 2 electrons. Because 2 electrons with opposite spins can occupy an orbital, both of helium's electrons are in the 1s orbital. The 2 electrons present in helium complete the filling of the first shell. This arrangement represents a very stable configuration, as is evidenced by the chemical inertness of helium. The electron configurations of lithium and several elements that follow in the periodic table are shown in Table 6.3. For the third element of lithium, electron of lithium, the change in the principal quantum number represents a large jump in energy and a corresponding jump in the average distance from the electron from the nucleus. It represents the start of a new shell occupied with electrons. As you can see by examining the periodic table, lithium starts a new row of the table. It's the first member of the alkali metals, group 1a. The element that follows lithium is beryllium. Its electron configuration is 1s2, 2s2, Table 6.3. Boron, atomic number 5, has the electron configuration 1s2, 2s2, 2p1. The fifth electron must be placed in a 2p orbital because the 2s orbital is filled. Because the 3 2p orbitals are all of equal energy, it doesn't matter which 2p orbital is occupied. With the next element, carbon, we encounter a new situation. We know that the 6th electron must go into a 2p orbital. However, does this new electron go into the 2p orbital that already has 1 electron? Or does it go into the other 2p orbitals? This question is answered by Huns rule. which states that for degenerate orbitals, the lowest energy is attained when the number of electrons with the same spin is maximized. This means that electrons will occupy orbitals singly to the maximum extent possible, so that these single electrons, as given a subshell, will all have the same spin magnetic quantum number. Electrons arranged in this way are said to have parallel spins. For a carbon atom to achieve its lowest energy, therefore, the two p electrons will have the same spin. For this to happen, the electrons must be in different p orbitals as shown in Table 6.3. Thus, a carbon atom in its ground state has two unpaired electrons. Similarly, for nitrogen in its ground state, Huns' rule requires that the three 2p electrons singly occupy each of the three 2p orbitals. This is the only way for all three electrons to have the same spin. For oxygen and fluorine, we place 4 and 5 electrons respectively in the 2p orbitals. To achieve this, we pair up electrons in the 2p orbitals as we see in sample 6.7. Huns' rule is based in part in the fact that electrons repel one another. By occupying different orbitals, the electrons remain as far as possible from one another, thus minimizing electron-electron repulsions. Section 2. Condensed electron configurations. The filling of the 2p subshell is complete at neon, Table 6.3, which has a stable configuration with 8 electrons, an octet, in the outermost occupied shell. The next element, sodium, atomic number 11, marks the beginning of a new row of the periodic table. Sodium has a single 3s electron beyond the stable configuration neon. We can therefore abbreviate the electron configuration of sodium as neon in brackets 3s1. The symbol brackets neon represents the electron configuration of the 10 electrons of neon, 1s2, 2s2, 2p6. Writing the electron configuration as the configuration of neon 3s1 helps focus attention on the outermost electrons of the atom, which are ones largely responsible for the chemical behavior of the element. We can generalize what we have just done for the electron configuration of sodium. In writing the condensed electron configuration of an element, the electron configuration of the nearest noble gas element of lower atomic number is represented by its chemical symbol in brackets. For example, we can write the electron configuration of lithium as lithium is the configuration of helium 2s1. We refer to electrons represented by the symbol for a noble gas as the noble gas core of the atom. More usually, these inner shell electrons are referred to as the core electrons. The electrons given after the noble gas core are called the outer shell electrons. The outer shell electrons include the electrons involved in chemical bonding, which are called the valence electrons. For lighter elements, those with atomic number 30 or less, all of the outer shell electrons are valence electrons. As we'll discuss later, many of the heavier elements have completely filled subshells that are not involved in bonding and therefore are not considered valence electrons. By comparing the condensed electron configuration of lithium with that of sodium, we can appreciate why these two elements are similar chemically. They have the same type of electron configuration in the outermost occupied shell. Indeed, all the members for the alkali metal group, 1A, have a single s valence electron beyond a noble gas configuration. Transition metals. The noble gas element argon marks the end of the row started by sodium. The configuration of argon is 1s2, 2s2, 2p6, 3s2, 3p6. The element following argon in the periodic table is potassium, K, the atomic number 19. In all its chemical properties, potassium is clearly a member of the alkali metal group. The experimental facts about the properties of potassium leave no doubt that the outermost electron of this element occupies an s orbital. But this means that the electron with the highest energy has not gone into the 3d orbital, which we might have expected it to do, hereby ordering the energy level in such that the 4s orbital in a lower energy than the 3d orbital. Hence, a condensed electron configuration of potassium is argon 4s1. Following the complete filling of 4s orbital, this occurs in the calcium atom, The next set of orbitals to be filled is the 3d. You'll find this helpful as we are going to refer often to the periodic table on the front inside cover. Beginning with scandium and extending through zinc, electrons are added to the 3d orbitals until they're completely filled. Thus, the fourth row of the periodic table is 10 elements wider than the two previous rows. These 10 elements are known as the transition elements or the transition metals. Note the position of these elements in the periodic table. In deriving the electron configuration of the transition elements, the orbitals are filled in accordance with Huns rules. Electrons are added to the 3d orbitals singly until all 5 orbitals have 1 electron each. Additional electrons are then placed in the 3d orbitals with spin pairing until the shell is completely filled. The condensed electron configurations and the corresponding orbital diagram representations of 2 transition elements are as follows. Manganese is argon 4s2 3d5. Zinc is argon 4s2 3d10. Once all the 3d orbitals have been filled with 2 electrons each, the 4p orbitals begin to be occupied until the completed octet of outer electrons 4s2 4p6 is reached with krypton. Atomic number 36, another of the noble gases. Rubidium marks the beginning of the 5th row. Refer again to the periodic table on the front inside cover. Notice that this row in every respect like the preceding one, except that the value of n is greater by 1. The lanthanides and actinides. The 6th row of the periodic table begins similarly to the preceding one. 1 electron into the 6s orbital for cesium, the 2 electrons for the 6s orbital of barium. Notice, however, that the periodic table has a break, and the subsequent set of elements 57 to 70, is placed below the main portion of the table. This place is where we begin to encounter a new set of orbitals, the 4f. There are 7 degenerate 4f orbitals, corresponding to the 7 allowed values of m1 ranging from 3 to -3. Thus, it takes 14 electrons to fill the 4f orbitals completely. The 14 elements corresponding to the filling of the 4f orbitals are known as the Lanthanides elements or the rare earth elements. These elements are set below the other elements to avoid making the periodic table unduly wide. The properties of the lanthanide elements are all quite similar, and these elements occur together in nature. For many years, it was virtually impossible to separate them from one another. Because the energies of the 4f and 5d orbitals are very close to each other, the electron configurations of some lanthanides involve 5d electrons. For example, the elements lanthanum, La, and cerium, Ce, and praseodymium, Pr, have the following electron configurations. Lanthanum, xenon 6s2 5d1. Cerium, xenon 6s2 5d1 4f1. Praseodymium, xenon 6s2 4f3. Because lanthanum has a single 5d electron, it's sometimes placed below yttrium as the first member of the 3rd series of transition elements. Cerium is then placed as the first member of the lanthanides. Based on their chemistry, however, lanthanum can be considered the 1st element of the lanthanide series. Arranged this way, there are fewer apparent exceptions to the regular filling of the 4f orbitals along the subsequent members of the series. After the lanthanide series, the 3rd transition element series is completed by the filling of the 5d orbitals, followed by the filling of the 6p orbitals. This brings us to radon, the heaviest of the known noble gas elements. The final row of the periodic table begins by filling the 7s orbitals, the actinide elements, of which uranium, element 92, and plutonium, Pu, element 94, are best known, and are then built up by completing the 5f orbitals. The actinide elements are radioactive, and most of them are not found in nature.